Hello, I'm Josh Starmer and welcome to my live stream. Bootstrapping sounds so complicated. Bootstrapping is not so complicated. It's StatQuest. Hello, I'm Josh Starmer and welcome to my live stream. I guess I got it backwards today. There's always something I mess up at the intro. However, I'm super excited to be here. And I just want to say I'm super excited about where everyone is watching from. We got people in New York, Pennsylvania, Malaysia, Mexico, Germany, Indonesia, India. Someone said nice hair. I just comb my hair a little bit. It's really long these days. I'm debating whether or not I should get a haircut this week because it's really getting long. And I just don't know what to do. I don't know if you got some advice, put it in the chat. Maybe I could cut it myself. I've thought about it. Oh, we've got South Korea, Montreal, which is super exciting. Virginia, we got some people in North Carolina, my home state, watching, which is cool. Moscow, China, all the way. Holy smoke, the other side of the world. Melbourne, Australia, Sweden, Japan, all over. Super exciting to have everyone. Jordan, holy smokes, all over the world watching a StatQuest live stream on bootstrapping. Oh, we've got Romania, Georgia, more India, Hyderabad, Iraq, Iran. Got that area covered. Wow. Colombia, India, Brazil. Oi, Brazil. Let your hair be, says somebody. Kerala, India. I love Kerala. What a beautiful place. Malta. Wow, I've never been to Malta. Argentina, Sicily. Oh, I'd love to go to Sicily. Morocco, Austin, Texas, Hungary. Hungary is where all the mathematicians live, isn't that right? Or at least historically. Bahrain, more Germany, US, Georgia, Portugal, Canada, more Brazil. Oi, Brazil. Vancouver, Canada, India, wow, Morocco as well. I had a friend from Morocco when I was in college. He was super cool. Jaipur, wow, okay, London, Chile, more Morocco, Bangalore. This is super exciting. All right, I'm gonna get started with the StatQuest. So let's move on. And we're going to talk about bootstrapping main ideas. Bootstrapping is a simple yet powerful technique that's used a lot in both statistical inference and machine learning. Bootstrapping may sound fancy, but it's not. That's the cool thing about it. Today we're going to go through an example that shows how bootstrapping can be used for statistical inference. The plan is for the next live stream, I think that'll be the first Monday in July, is to then show how it can be used in machine learning. Bootstrapping is kind of a cool thing that has a wide variety of uses and has kind of been the savior of statistics catching up with machine learning. Machine learning is moving so fast. But one thing in statistics that's been able to keep up with machine learning has been the bootstrap. Okay, so without any more jibber-jabber introductory nonsense stuff, let's get started. Okay, imagine we had a new drug to treat an illness. And we gave that drug to 8 different people that had the illness. For 5 of those people, the drug helped them feel better. But for 3 people, the drug made them feel worse. Wah, wah. Okay, if we calculate the mean of the response to the drug, we get 0.5. 0.5 isn't a huge improvement, but since most of the people, 5 of 8, improved, maybe this drug is better than using no drug at all. However, maybe those 5 people, maybe these 5 people, let me just change that while we're at it. Okay, maybe those 5 people all felt better because they were healthy to begin with. And maybe these 3 people all felt worse because they had unhealthy lifestyles. So it's possible that the reason we got a mean value equal to 0.5 instead of 0 is because of random things that we can't control. So we create a hypothesis. On average, the drug has no effect on whether people feel better or worse. In other words, the hypothesis says that the only reason we see a difference between the mean of the data, 0.5, and 0, is due to random chance. Now we need a p-value to decide if we should reject the hypothesis. There are a lot of ways to calculate p-values, but today we're going to use bootstrapping. Bam! Okay, first, before we start doing the bootstrapping, what we're going to do is we're going to shift all of the measurements to the left, 0.5 units, so that the mean is shifted to 0. Yeah, so all we did is we just moved those 8 measurements over 0.5 units, so now the mean is centered right on 0. Okay, now we can calculate a p-value by applying the bootstrap to the shifted data set. First, itchy nose, feels better now. Okay, first, let's make a new number line. And from the 8 measurements that are centered on 0, choose one at random. And add that value to the new number line. Now we go back to the original 8 measurements that were centered on 0 and choose another random value. And add it to the new number line. Then we repeat the process, randomly selecting one of the 8 values centered on 0 for the new number line a total of 8 times. Note, we can randomly select the same value more than once. Oh no! It's a terminology alert! Randomly selecting data and allowing for duplicates is called sampling with replacement. It's one of the key things that makes bootstrapping what bootstrapping is. That's an awkward sentence. Let me rephrase that. Sampling with replacements is one of the key aspects of, and it makes bootstrapping, it's what makes bootstrapping bootstrapping. Maybe words aren't my specialty today. It's a key aspect of bootstrapping. Okay. Anyway, so far we've only selected 6 measurements, so we need 2 more. Beep, boop. Note, the reason we selected 8 measurements for the new number line is because the data set we are sampling from contains 8 measurements. If we'd started with 10 measurements up here, then we would have needed to add 10 measurements down here. Terminology alert! Oh no! This new data set that was created using sampling with replacement so that it had the same number of values as the original is called a bootstrap data set. Okay, now that we have a new bootstrap data set, we can calculate the mean and add that mean to what will soon be a histogram of means. So it's not much of a histogram yet because we've only added 1 value to it, but we're going to add more stuff to it, and over time it's going to look like a cool histogram. Okay, now we start over with a fresh number line and randomly select one of the 8 values centered on 0 for the new number line, repeating a total of 8 times and allowing duplications. Beep, boop, beep, boop, beep, boop, beep, boop. Then we calculate the mean and add that to our histogram. Note, this process of creating a bootstrapped data set and then calculating something, in this case we're calculating the mean, and keeping track of those calculations is called bootstrapping. No big deal. In other words, bootstrapping consists of 3 steps. 1. Make a bootstrapped data set. 2. Calculate something. In this case, we calculated the mean. 3. Keep track of that calculation. Note, in step 2, we calculated the mean, but we could have just as easily calculated the median, or the standard deviation, or anything else we wanted to test or learn more about. Later on, I'll say why this flexibility is awesome. For now, I'll just say, BAM! Okay, now that we know what bootstrapping is, we just do it a bunch of times. Usually we use a computer to bootstrap thousands or 10,000s of times. I'm not going to go through every single one. We're just going to skip to the histogram. Okay, so after creating thousands of bootstrap samples, calculating their means, and adding them to this histogram, we end up with this. Because we sampled with replacement, the histogram ended up with a wide variety of mean values. For example, all these different values are in this bin in the histogram. And because we are randomly selecting with replacement from 8 values, they are up to 8 to the 8th, or 16,777,216 combination of observed values and possible means that we could put into that histogram. Because there are so many combinations, bootstrapping usually only creates a subset, like 10,000, to estimate the full distribution. In this case, because we created the bootstrapped samples from a collection of measurements with mean equal to 0, then the histogram tells us how the means from each bootstrap sample are distributed around 0. In this case, because 36% of the bootstrapped means were between negative 0.5 and 0.5, the probability of observing a mean between negative 0.5 and 0.5 is 0.36. So the percentage is essentially the probability. The percentage of observations in a region in the histogram equals the probability that you'll get a randomly selected mean or bootstrapped mean in that range. And because 16% of the bootstrap means were less than or equal to negative 0.5, the probability of observing a mean with a value less than or equal to negative 0.5 is 0.16. And because 48% of the bootstrap means were greater than or equal to 0.5, the probability of observing a mean with a value greater than or equal to 0.5 is 0.48. Yeah, that's right. Bam! I just wanted to double check that I didn't have a big mistake right there, but I think we're all good. Okay, cool. Okay, now let's finally go back to the original sample and focus on its mean value, 0.5. Because we wanted to know if we got 0.5 instead of 0 because of random things, like maybe these people had healthy lifestyles and maybe these people had unhealthy lifestyles, we formed this hypothesis. On average, the drug has no effect on whether people feel better or worse. Then we shifted the sample over so that it was centered on 0. So there it is, centered on 0. Bam. And then we use bootstrapping to make this histogram of means. And because the shifted sample is centered on 0, the histogram represents possible values for the mean if the drug, on average, made 0 difference in how people felt. So the p-value for the observed mean, 0.5, given this histogram that represents the hypothesis that the drug had 0 effect, is the probability of observing a bootstrap mean that is greater than or equal to 0.5, which is 0.47, that's the probability, plus the probability of observing a bootstrap mean less than or equal to negative 0.5, which is 0.16. Adding those two probabilities together gives us 0.63. And because 0.63 is greater than 0.05, we fail to reject the hypothesis that the drug makes no difference. Double bam. Okay, now let's quickly review the bootstrap. Bootstrapping consists of 3 steps. 1. Make a bootstrap dataset. 2. Calculate something. In this example, we calculated the mean, but we can calculate other things like the median or the standard deviation. 3. Keep track of that calculation. Okay, now let's talk about why step 2 leads to awesomeness. First, let's go back to the original data. Last time we calculated the mean and then shifted the data over so that it had mean equal to 0. And then used bootstrapping to create this histogram of means around 0. And then we used the histogram to test the hypothesis that the drug made 0 difference. However, we could have just as easily calculated the median for the original data and shifted the data so the median equals 0. And then used bootstrapping to generate this histogram of median values around 0. Note, that's a funky looking histogram, but it tells you that, medians have strange distributions, and that's why we don't often use them in statistics. Although they are great because they're resistant to outliers, they've got weird properties, and we can see that sort of in this histogram. But with bootstrapping, who cares? We just generate this distribution, and we can use the histogram to calculate the p-value for the observed median, given the hypothesis that the drug has 0 effect. In this case, the observed median is 1.8. So the p-value for the observed median, 0.8, given this histogram that represents the hypothesis that the drug has 0 effect, is the probability of observing a bootstrapped median greater than or equal to 1.8, which is 0.01, plus the probability of observing a bootstrapped median, which is less than or equal to negative 1.8, which is 0.19. And when we do the math, we get 0.2. So again, we would fail to reject the hypothesis that the drug has 0 effect, but this time we use medians instead of means. And the point of this example is that we can use bootstrapping to test whatever we want. And that means that if our data looks like it has outliers, we can use medians, which are more resilient to outliers than averages. Triple bam! Okay, usually triple bam means we're totally done, but before we're done, I want to mention a few more things and make some shameless self-promotions. Okay, although we first shifted the data sets before bootstrapping to calculate p-values, we could have just as easily bootstrapped the original data set and created a histogram of means or medians or whatever just using the original data set. And then we can use the histogram to calculate the standard error of the mean, or if we use the median, we could calculate the standard error of the median, or if we calculated the standard deviation, we could calculate the standard error of the standard deviation. Or we can use this histogram to calculate confidence intervals around the mean. The standard error is just the standard deviation of this distribution, so that's easy. And a 95% confidence interval is just an interval that covers 95% of the bootstrapped means or medians or standard deviations or whatever. No big deal. Shameless self-promotion. For more details about using bootstrapping for confidence intervals or standard errors, check out these quests. These are some like prehistoric quests. These are from Years ago when I was just starting out making these videos to begin with. So in some ways they're classics, in some ways they're clunkier than my new ones, which are still pretty clunky. But these old ones are kind of like old gems. If you want to see me like completely like unscripted and just sort of winging it, check out these videos. Anyways, with that, we're done with this StatQuest. So we've got a little extra time on our hands. And so what I'm going to do is I'm going to go over to the chat window and I'm going to see if we got any questions. I know we got a lot of people from calling in, or not calling, watching from all over the place, which is super cool. Let me see if I missed anyone before. Chile, Morocco, Bangalore, Selapura, interesting. Austria, Turkey, Wales, Thailand, Eugene, Oregon, Poland. Hello, Poland. All the world here. Gujarat, Bangalore, Mumbai, Vietnam. Good morning, Vietnam. Mexico, New Delhi, Algeria, more Korea. What else? Pune, Nepal. Hello, up in Nepal. I went to Kathmandu a long time ago when I was 10 years old, and I loved it. More Russia. Okay. What else do we have? Do we have any good questions? Why we shifted before the bootstrapping? So the only reason in this example, because we wanted to calculate p-values, let's go back to this. The goal, we wanted to calculate a p-value for the red mean. We wanted to decide if the observed mean, the light just went out, so it's a little darker in here. We wanted to know if the observed meaning, 0.5, if the only reason why it's different from 0 is due to random chance. And so what we want to do is we want to create a distribution of means around 0 to see how rare or rarer similar means might be to what we observed with the real data. So that's why we're shifting things over. We shift things over so that when we create this histogram down here, when we create this histogram will be centered on 0, and that histogram will then tell us how means are distributed around 0, and we can then go back and look at the original mean that we calculated up here, boop, 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 right here, that original mean, and we can see that when we have means centered on 0, it's actually pretty common to have means centered around 0 to still be pretty far away from 0. And because that's pretty common, we don't have any confidence that the observed mean 0.5 is super special anymore, so we fail to reject the hypothesis. So that's why we shift. However, I want to make a point that shifting is only necessary when we want to test the hypothesis that there's no difference. And if you want to know more about hypothesis testing, check out the last live stream that we did. You can go to statquest.org and there's a link to the video index. And at the very bottom, I've got all the live streams. You can go down to the live stream and you can check out hypothesis testing. And that's when you'll find out why we're interested in testing if there's 0 difference. Let's see if we got some more questions. Someone asked if I have a video on backpropagation, and I'll just tell you right now, absolutely not. However, I'm working on it. Backpropagation is all about neural networks, and neural networks that backpropagation algorithm is based on being able to do the chain rule, and then applying gradient descent on the derivative of these activation functions. So we use the chain rule from high school calculus, which for some people was a long time ago. And so what I'm doing right now is I'm doing a video on the chain rule. And maybe not the coolest of topics, but it's one of these things that if you understand very well and very deeply, understanding back propagation, understanding back propagation will be a snap. So what this video on the chain rule is a stepping stone. So we're going to get the chain rule out of the way, and then we're going to cover back propagation and neural networks. And we're going to look at that and go, hey, I'm so solid in the chain rule because I watched the StatQuest on it. And now when I'm seeing this thing on back propagation, it's all super easy and obvious. So we're getting there. We're going to get to back propagation sooner or later. I'm excited about that. Somebody else said bootstrapping triggers my statistical computing course, and that is exactly right. Bootstrapping is all about statistical computing, but it's also, like I was saying early on, bootstrapping is sort of, because it's so adaptable and so flexible, and we don't have to like come up with some theoretical distribution. We can always just bootstrap and create the distribution on the fly. Bootstrapping is a modern technique that uses computers, but it allows us to just kind of generate new statistical tests on the fly without having to spend years and years doing theoretical fancy stuff. What else? Do we have any more questions? I'm still just scrolling through. Bootstrapping, someone asked if it's related to the bootstrapping used in structural equation modeling, and it's very similar. And we're going to be talking about how bootstrapping is used in machine learning. It's used in a slightly different way, but also a very related way. Obviously, when we're doing statistics, we want to calculate p-values and confidence intervals. And when we're doing machine learning, maybe we want to do those things plus something else that's also interesting. So we'll see how this bootstrapping concept in our next live stream, which I think will be the first Monday in July, we're going to see how this concept can be applied in different settings, kind of doing different things. Someone asked if we should shift to any other point estimates. It just depends on your hypothesis. Whatever your hypothesis is that you want to either reject or fail to reject, you shift it to that. So say like our hypothesis was that this drug should have a mean response of 5. Well, then we'd shift everything so that the mean of the original data was now over 5. Coming up with hypotheses like that is a little bit of a crapshoot, and sometimes people do it. Most of the time, however, we do what's called the null hypothesis, where we just shift everything to 0. However, if you've got a special hypothesis, go ahead, shift your samples over to that special mean. Someone asked if we can do support vector machines next time. I've actually already got StatQuest on support vector machines, so if you have specific questions about those, watch the videos. You can find them on my channel, or you can find them on the statquest.org website. Again, go to the video index, and then you can just search the page. There's a ton of videos on that page. They're kind of organized from simple to complicated, and I've bracketed them in statistics up top, and then below is machine learning. So you're going to go down to the second half of that page, and you're gonna find support vector machines, and you watch those videos and you post questions there, and if there's a bunch of good questions that I can't answer in those little tiny comments, we can bring it up in a live stream. But check out those videos first. Someone else says how do you do any implementation of bootstrapping? If not, would you do it for us? Thanks. So yeah, bootstrapping is such a simple algorithm. Most programming languages that do data analysis, like R, or I'm pretty sure in scikit-learn, or not scikit-learn, but scikit in Python, or NumPy or something like that, there's a function that will do the bootstrapping sampling for us. And so then it's a very simple, like 2-line for loop. So for, 1,000 or 10,000 iterations, create a bootstrapping data set, calculate the mean or the median or the standard deviation or whatever it is you want to calculate, save it in an array, and bam, So I guess that's a 3-line for loop. So it's not that big a deal. Someone asked why we're using both tails if we're evaluating 0.5 as our mean. Why we're doing a two-tailed test. And the reason why we're doing a two-tailed test is I love two-tailed tests, and I actually talk about that in my video on how to calculate p-values. So if you haven't seen that video, you may already know how to calculate p-values, but if you go to the end, YouTube now has these chapters, and you can actually, if you hover your mouse over the timeline on the bottom of the video, there's a chapter where I describe why I like two-sided p-values so much. So just go to that part of the video, check it out. You'll understand why. Someone says the idea of bootstrapping sounds like bagging. And there's a good reason why it sounds like bagging. That's because bagging is short for bootstrapped aggregate. So if you take bootstrap and the word aggregate and you jam them, aggregating, and you jam them together, you get bagging. So if you're familiar with random forests, we do bagging in that, and that means we use bootstrapping to generate data sets that are the same size as before. So we do that in random forests, we do it in AdaBoost, XGBoost, a lot of machine learning algorithms will apply bootstrapping in some way, and we'll talk about that in the next live stream, which I believe will be the first Monday in July. So that's what we're shooting for. All right. Well, we've been here for 30 minutes. I don't want to be talking all day. I'm really excited you guys are all here. It means a lot to me that you join me for my live stream. Until next time, quest on.